Associate Professor Susan Rowland was a Human Frontiers in Science long-term postdoctoral fellow at the University of Connecticut and is Chair of Teaching and Learning in the School of Biochemistry and Molecular Biosciences. She's the Editor-in-Chief of the University of Queensland's Science Undergraduate Research Journal and the host and co-producer of Free Energy Radio, a project that aims to bring the voices and lives of working scientists to the student body at the University of Queensland. So Susan, can you tell us what is the relationship between thinking skills and science?
Thinking skills and science. Science, the very top level of science, is really about being able to ask a question, which is a new question, being able to put up a hypothesis about how you might address that question and what you're expecting to get, and then to be able to test that hypothesis and then integrate what you find back into the larger body of knowledge. That's extremely high level science. There are a lot of thinking skills underneath that. There's the ability to memorise a bunch of stuff, which as scientists we rather enjoy. That's our content base where we feel very strong and comfortable. There's the ability to analyse the important components of what you're looking at, to compare and contrast and make really critical decisions about what you need to know. And then the other part of science is being able to tell a story, so thinking about what is important to your audience. And that audience can be either the public or other scientists.
So for other scientists, how significant is it that science is essentially a social
It's
way of
enormously important. Science is never done in a vacuum. This idea of the lone scientific genius, which has been around for a long time and it's very romantic, it really doesn't happen anymore. There are a number of reasons for that. The first reason, I think, is because science is supported by the public. It's paid for by the public, so our grants are public money. So we have an enormous responsibility to the public to spend their money wisely. When you go to get a grant, you have to make sure the very first thing that you do when you're writing a grant is to say why it's important to the public. Why should the government spend the public's money on what you're doing? So when you think about that, you think about the value to everybody, and that becomes a very social enterprise. But then, of course, the other thing is that you can't come up with all the good ideas for yourself, and you need to talk to other scientists and work with them on problems. This idea of coming up with a hypothesis, you very often don't do that by yourself. You talk with other people in your lab, you talk with colleagues in your department, you talk with friends who are outside your general area, and you think about, again, what's important to the scientific community. You also read the literature, which has come from many other people. And you think about your questions that way, and you think about the approaches that you can use. The other thing is that you can't do all the work alone, because you can't possibly have all the skill sets that you need these days. Again, it used to be that you could do science that was very isolated and used one technique, but now reviewers and journals expect a lot more than that. They expect multidisciplinary work, and it's very hard to get published without multidisciplinary work. So we work together in big communities.
You make the interesting point that you have to, in applying for grants, explain the value of what you're doing, which is, in a sense, a philosophical requirement that you need to talk about value.
Yes.
And all this. Is this idea of value commonly shared among scientists?
Very much so, yes. In science, you don't do it for the money, and you don't necessarily do it for the glory. You do it for two things. You do it for the sense of discovery, the excitement of learning something new, but the other reason you do it is because you want to give something to society. Sometimes that's selfish. You think, oh, I want to make this great discovery and I want people to know me for that. But primarily what it is about is addressing a problem. It might be somebody with a terrible skeletal disorder. You may want to understand how it is that the skeleton decides to lay down bone in the wrong place. You can help alleviate suffering doing that. It may be that you want to understand what's happening with organisms that are in the permafrost. You might want to understand how much methane they're going to produce. How is the environment going to heat up? Somebody has to find that out. It's going to help us in terms of our long-term planning on the planet. So it's extraordinarily important, and I think that's really what drives people, that sense that they're going to be doing something that helps the planet.
So the conclusions we might reach in terms of what actions to do, which might be value-based ones, need to be informed by what science can tell us.
Absolutely.
It's always an interesting question to think about science and thinking, and in as much as that might be critical thinking, how has science institutionalised or through its methodology captured some of those key ideas of how to think well?
How to think well? Well, that's a good question. I think in science, you need to be able to test something. If it's not testable, then it's pseudoscience. Right? So pseudoscience or pseudoscientists make claims that are very broad, and if you try and argue about the claim, they will say, oh, well, it only works for certain people, or it only works in the Northern Hemisphere, or whatever, right? But in science, you actually tend to make a very small claim, and you tend to address that claim very critically, very carefully, actually with a lot of self-doubt, and often quite tentatively. You have to test that claim in a controlled way, in a way that can be replicated, in a way that once you make a claim, a statement about what you've found, it's a generalisable claim. And that can often take a really long time and a lot of effort, years in some cases.
If science, has thinking in terms of testing hypotheses and that type of thing, what's the value of doubt in science?
Oh, doubt is everything. Doubt stops you making claims that are too big. There are a few things related to doubt. I guess the first thing is your personal fear that you've got it wrong, because as a scientist, you pride yourself on getting it right. You pride yourself on being exacting and careful, and it's part of your professionalism to be exacting and careful, and there's nothing worse than a sloppy scientist. But of course the other thing is that there's the very public embarrassment of putting something out there that's wrong. There are obviously instances where people actually fabricate data and then publish it, and then of course once they're caught, their entire career is destroyed, and the ripple goes a lot further than that individual. So there's a responsibility to yourself, there's a responsibility to the scientific community, and there's also a responsibility to the people who are funding you and the people who are going to use the data that you produce. So doubt, absolutely key. You're always questioning yourself.
So can you be ever sure that you're absolutely right?
No.
That was a quick answer.
You can't.
Yeah.
You can't. There's always the possibility that it's not right. And I guess that's the other thing, the other difference between science and pseudoscience. If it's pseudoscience, you will claim that it's right, and it's not questioned. It's very interesting now when I'm teaching now, in comparison to what I learnt when I was an undergraduate. When I was an undergraduate, I thought that what we were learning in lectures was right. It was all that was known, and I used to sit there in lectures thinking to myself, everything's known. How can I possibly find anything to research? Because it all seems to be so known and so sure. And then, of course, I realised that that wasn't the case, that all what we were being taught was the best explanation of what we knew at the time. Now, of course, what we teach is still based on what we knew then, but it's very much more advanced, much deeper, and in some cases what we learnt was wrong. So I'm very careful to point that out to my students now. And I often ask them, do you think there's another explanation for this? Do you think that there's everything that we know is what is here? Do you think that there could be other questions that we could ask? And I'm constantly reassuring the students that there are other things to work on in science.
What's the value of questioning in science? Associated, I guess, with doubt, but what's the value of coming up with the right question?
The right question, there are two things. First, the right question is very exciting because it gives you a whole new impetus, a whole new... actually, often when we're writing grants, that's when we come up with the question. We will often have a sort of a vague question in our minds, and then as we read the papers, the other literature, and we start formulating what we'd like to work on, and we start developing that argument for value, the question becomes refined in our minds. So that's one part of the question, but I guess the other part of a good question, apart from it having value, is that it's actually something you can test. So you can have a very nice question. Particularly now I do educational research, I've discovered that quite a lot of questions that you can ask, you can't actually test because you have too many variables in them, too many things that you can't control. So the question forms the fundamentals of how you're going to do your experiments.
What sorts of questions can science answer, and what sorts can't it answer?
Science can answer questions that involve something that you can observe, or an effect, something that has an effect that you can observe, and it's a consistent effect, a reproducible effect. You have to be able to measure that, so there has to be some kind of equipment or method that you can use to measure it. And actually this is where a lot of our advances in science come from, is improvements in technology that allow us to measure things that we couldn't measure. I mean, the Higgs boson, for example, 20 years ago you couldn't have measured the ripples in space that are involved and associated with the Higgs boson, but now you can. MRI machines, another example. MRI machines actually look at the water content in your body. 40 years ago, we didn't have the technology to do an MRI, so we can now observe things that are very different to what we could observe 20, 30 years ago. What questions can we not answer? Questions that involve faith, questions where you have to believe something and there's nothing that you can test. Questions where if you have a doubt, there's nothing that you can do to address that doubt.
What then would you say would be the limits of science? How far can we go in understanding the world through science?
Limits of science. We're always limited by our technology, always limited by what we can observe. And that's where a lot of the money goes in scientific research, is to buy equipment that can detect things that are more and more subtle. And also to measure things with more and more accuracy. Limits. We're really limited by the technology. That's really it. Right? But any time you have to say you just have to believe it, or it's just a mystery, and that's as far as it will go, something you can't observe, that's a limit.
Do you think science is generally well understood? Not necessarily the facts of science, but the processes of science. Is this generally well understood?
No. One of the big issues with the processes of science is doubt, as we've been discussing. People inherently don't like doubt. Scientists are adventurers. Right? They spend a lot of time going, what if? I wonder what happens if I do this. What if I turn on this switch that I've already got an electric shock from? What if I do it again? Because you want to test it. You want to see if it happens twice. Right? You actually enjoy that sense of adventure and mystery. You enjoy the sense that there's something bigger than you, and that it's you stepping into the unknown every day, really. But it's not a comfortable place for a lot of people. I guess as scientists, we also feel that we have control over that unknown because we are investigating it. So in a way, we're trying to pin it down and solve a mystery. But if you are a person who doesn't have access to the equipment or doesn't understand the process, that unknown is quite unsettling. It's much easier to say, I'm not going to vaccinate my children because it causes autism. Whereas a scientist will say, there is no evidence. The chance that you will cause autism in your children by vaccinating is extraordinarily tiny, so small that we probably can't even measure it. And yet, that so small that we can't even measure it in somebody's mind may well be enough. So there's an understanding, I guess, on the part of scientists about the likelihood of things, which is not always apparent to the general public. And when a scientist says it does not happen or it does happen, we are more than 100% sure. We are at 1,000% sure if that's possible. If we say it will probably happen. We're probably 95% sure that it will happen. That level of grey, I think it's very uncomfortable for a lot of people. Whereas a scientist understands what the grey is.
Comfortable with uncertainty.
Yes.
That's an interesting idea. There are people who don't understand science particularly well, but you've suggested there are people who are actively anti-science as well. Are people, or are there, let me start the question again for that. Are there groups of people who are actively anti-science?
Yes. I guess there are, yes. Why would you be anti-science? Fear? I think a lot of the time people who are anti-science are afraid. Greed. If you can make money out of something that's a non-science or a pseudoscience by preying on other people's fear and greed in a lot of cases, then it's worth it to be anti-science. As a scientist, I understand why people are anti-science. I don't agree with it, but I understand it. And a lot of the time, if people are anti-science, I've certainly encountered people who are anti-science in the real world, and you can't change their minds because for them it's an article of faith. Yeah. Or it's driven by a more visceral emotion than logic.
What are some of the key examples of pseudoscience, and how can you tell when something is a pseudoscience?
Key examples of pseudoscience. So a key example of pseudoscience is the anti-vaccination debate. That debate is actually based on a paper that was published a long time ago and is now discredited and has been discredited in multiple studies. But it was a paper where they showed a link between the use of mercury-containing vaccines and the development of autism in students. Now, it turns out now that the data were definitely misinterpreted, perhaps even fabricated. I don't want to go too far in accusing somebody, but it was not correct, and it's been well shown that it was not correct, and yet people choose to still believe it. And when people believe something like that, they will bring up isolated incidents that they know of to prove their case, and that's really a hallmark of pseudoscience, is that it's not generally applicable, and yet when you challenge it, they'll say, oh, I know somebody whose son got vaccinated and then they became autistic. Now, that child might have become autistic anyway, but of course you can't do that controlled experiment.
Which is what separates anecdotal
Which is what separates anecdotal pseudoscience from science. I guess another thing that, well, rocks, crystal healing, that's certainly a pseudoscience. I was just looking up amethyst before I came. I thought I'll just look up the power of amethyst. Amethyst, apparently, if you read the pseudoscientific literature, creates patience and calm. It also allows you to increase your psychic capacities and communicate with angels.
Angels?
Yes. Now, of course, scientifically, we can never test that claim because we generally don't have an observable communication with angels. And we generally don't have any proof of psychic capacities. I mean, psychic capacities were another huge thing in the 80s. And Uri Geller was out there bending spoons with acid and all that kind of stuff. And I remember when I was a kid, everybody testing their psychic capacities. I used to try and test my, telekinetic powers. I could never move anything. It was very disappointing. But, that kind of psychic ability, again, you can't test it. So it's pseudoscience.
So I could tell you that I talk to angels, and you've got no way of disproving
exactly
that. Because there's nothing to measure.
I can't observe you doing it. You can tell me you're doing it, and you may well be doing it. Your brain chemistry may tell you that you are communicating with angels. So in your mind, it may be real. I mean, certainly for people who see visions, or people who would be diagnosed as schizophrenic, or people who are not diagnosed but see and hear things. In their minds, often those things are very real, but we can't observe it. So what we can say is that it's a psychiatric issue. It's not a scientifically proved idea.
Do you think that the fact that people can experience things subjectively with great force is one of the reasons why they might turn against science, which demands more objectivity?
Yeah. Yeah, you're right. I hadn't thought about that before. But yes, I think they could. I mean, certainly before we understood clinical psychiatric treatments, and by that I mean treatments that involve drug use for people. Before we understood things like porphyria, before we understood depression, before we understood bipolar disorder, and we understood that they are actually biochemical imbalances, before that, these things were unexplainable, observable on the outside by behaviours that were very unusual, but for the person who was experiencing them, extraordinarily powerful. Dreams, another thing that people can experience, and then a dream might come true, perhaps by accident. But again, we can't see the observable facts on the outside, but the person experienced it very, very intensely. So yes, I mean, I can imagine that would make them turn against science if somebody said, well, that's not possible. And they said, but it is possible for me.
So when someone reports a very strong subjective experience, if the scientific evidence is that they're not having that experience, they obviously will refute that. They'll say, well, that's
you're quite right.
That's not right.
Yeah. Yeah. I mean, personal experience is the most powerful thing that we have.
This is an interesting idea because it goes to the idea of social verification of knowledge and science as a manifestation of that. So in what sense can you say that science socially verifies knowledge?
Well, we say in science, if it's not published, it didn't happen. So you can have all the results in the world in your lab, but if you can't get them into a peer-reviewed journal, they're worthless. Publication is the metric that we use in science for success. And so it's very heavily socially scrutinised, science. And if you can't get it published, then people aren't going to believe it. So I guess it's 100% dependent on social verification. It's 100% dependent on peer verification. And that's, again, why we have to be so careful in the way we do our experiments and why we doubt ourselves so much.
What's the value of reproducibility in science?
The value of reproducibility? Oh, it's enormous. If you can't reproduce something, again, it's worthless. There's a very interesting paper, actually, that I've been teaching my students about quite recently because in this unit that we're working in, we're thinking of the process of science and reproducibility of science and the frustration associated with being able to reproduce things and not reproduce things and the social issues associated with that. Certainly, many of the early scientists would do experiments that others couldn't reproduce, often because they were being done with either bad equipment or bad hypotheses. And then what has happened over time is that our equipment has become more standardised. The chemicals that we can get are now completely pure, whereas before scientists would have just prepared their own. So you can now buy all of the reagents and all of the equipment that you need off the shelf to do your experiment. So technically, one person should be able to do it in one place, and another person should be able to do it in another place, and it should come out the same. Now, if you have a situation where you're using something that has a variable in it, a mouse, for example, you're using different mouse strains to try and do the same experiment, and you can't get the same results from one mouse strain to the other, you have to ask yourself very carefully what's going on. The first thing you do, I've been in this kind of situation, not with mice because I'd never worked with mice, but with bacteria. The first thing you do is you go to the other people and you ask them for their reagents. You say, what company are you using? How did you prepare this? Sometimes they share with you and sometimes they don't. It depends whether you're competing or whether you're friends.
Sometimes it's a social process.
Sometimes it's a social process and sometimes it's a very anti-social process, yes. But if they're willing to share everything with you and then you come back and you do the experiment again and you still can't get it to work, the next thing you say is, then I'll try their kind of mouse. Right? You probably would have done that first, actually. So try their kind of mouse, their reagents. If you still can't get it to work and it should be all exactly the same as what they did, you start to ask some really serious questions. Who's wrong? One of us must be wrong. And then you start trying the experiments with other mouse strains and other reagents, and you start asking other people around, can you get this to work? You know, I can't get this to work. And again, this ripple of doubt starts to spread out, and people start asking questions that can be quite embarrassing. So reproducibility is enormous. That the social pressure to make sure that you've got the experiment right.
We know that we are subject to quite a few cognitive biases, like the confirmation bias, where we seek to confirm what we think
Yes.
rather than falsify it.
It's very frustrating when you're a scientist and you can't confirm it.
Well, how does science deal with that? What about the methodology of science allows you to deal with cognitive biases like that?
So we always do experiments that are controlled. So we will, by and large, in an experiment, we will set up a positive control that we expect to work and a negative control that we do not expect to work, and then we will set up our experimental system. Simple example, say you've got some bacteria and you want to put a plasmid into them. This is a little piece of DNA. You want to put this little piece of DNA into these bacteria, and the piece of DNA has got a special gene on it that gives the bacteria some kind of power, drug resistance. Right? If you were doing your test and you wanted to test a new gene to see if it gave drug resistance, you would take 3 lots of bacteria, you would get 1 lot of bacteria and you would put the piece of DNA in that you knew gave resistance. You would take another set of bacteria, you would put another piece of DNA that didn't give the resistance, so that's your negative control, the other one was your positive control, and then you'd do your test, which would be your bacteria, where you would put a piece of DNA that you are hoping that will give the resistance, but if it doesn't, that's okay because you've tested it, right? And then after you've put those 3 pieces of DNA into those 3 sets of bacteria, you put them on a medium that challenges them and says, you can't grow unless you have this particular power. So that's what we call antibiotic selection, right? Now, even though we want that piece of DNA to give that property, if it doesn't, it doesn't. But we've set up our positive and negative control so that we know that our method worked.
Despite your own biases?
Despite our own biases, the methods work because this one shows up with the cells all growing, this one shows up, no cells grow at all, and then on yours, no cells grow. It's very sad. Of course, you try the experiment several times to say, well, maybe I didn't do the transformation properly. Maybe I didn't put the DNA in properly into the cells. But after you've done it several times and failed, you have to admit that your wish for it to work is not going to be fulfilled.
Can you explain a little bit about the process of peer review?
Peer review is a good thing and a bad thing. It can be brutal, but it can be enormously helpful. So what happens with a peer review is all good journals are peer reviewed. So when we say a good journal, we mean a journal that we would pick up a paper from it and we would believe it. We would read it and go, yep, I think this is okay. I can base more work on this. I can cite this paper in a grant application or in my papers. I can continue with this and I believe I'm on solid ground. Because the last thing you want to do is start doing experiments based on work that's just out there in the community, but nobody's checked it. Right? Peer reviewing is a way of checking. So the way you get a peer review done, you write your paper, you collect all your data, of course, first, which can be many years of data. You write your paper, you produce all of your diagrams that show all of your results. You write an introduction and a discussion which cite all of the relevant literature and explain where you got your ideas and what foundations you're building on. Then you show all of your results. Then you have your discussion and conclusion, and that shows what you found, where you think you can go with this from now on. Then you send it to your chosen journal. And what the editor of that journal does is send it out to people that they think are experts in that field, peers. And then those people read it, and what they have to do is give comments, and they have to judge whether that paper should be published or not. And they give a lot of feedback generally, sometimes very tough feedback to deal with. Again, this personal doubt. Once you get the reviewers' comments back, you have to act on those. You have to write, the editor will send it to you. Now, several things can happen. The reviewers can recommend that your paper just be rejected, which is very sad, but it happens a lot. The reviewers can recommend that you make minor changes. That's great. The reviewers can recommend that you make major changes, which is depressing, but okay. And they can reject. Or sometimes they can just say, we're just going to publish as is, which is incredible. I've had that happen once, I think. So then you get it back. You have to decide what you're going to act on. You've got a few ways you can go. You can make the changes that they request, which can often be going and getting a lot more data, maybe another year or two worth of data, at least a few weeks, usually months to years. You can decide to rewrite the paper and send it to a different journal, which may have different reviewers, less exacting reviewers, less aggressive reviewers. You can abandon the work, which happens sometimes. Or you can just pop open a bottle of champagne and say, yes, it's been accepted.
Well, congratulations, yeah. Science is a body of knowledge, among other things, but that body has certainly grown a lot in the last few hundred years in particular. What's characteristic about the growth of knowledge in science? How does the growth of knowledge happen?
The growth of knowledge is absolutely predicated on the idea that what's come before you is carefully checked, that it's as right as it can be, that the data are reproducible, so that if you propose a new idea based on the stuff that has come before, you can be sure that you're on pretty solid ground. I guess with pseudoscience, if you propose an idea on what has come before wasn't checked. It's belief. So if you make a new idea, propose a new idea that is based on belief rather than fact as far as we know, it's very hard to build on that because it's not really logical, it's just conjecture. So I guess the difference is that science grows through a logical progression of ideas.
All right, that's a good thing to have, I think. So Susan, thank you very much for coming along and sharing that with us.
Thank you for having me. It's been fun.